Hi, I'm William Cotton, and this presentation is done in partial fulfillment of the requirements of CS 6263. The presentation introduces a recent study titled Collapse Like a House of Cards, Hacking Building Automation Systems Through Fuzzing. It addresses growing concerns around the cybersecurity of building automation systems, or BASs. As digital infrastructure becomes more pervasive, the systems that manage modern buildings, responsible for critical functions like HVAC, lighting, and access control, have emerged as vulnerable targets for cyber threats. The study proposes a new tool called BASE, which is short for Building Automation System Evaluator. BASE applies protocol-aware fuzzing to evaluate the security of BAS networks. Unlike traditional fuzzers, BASE was built specifically to handle the unique characteristics of BASs: proprietary protocols, closed-source software, timing-sensitive communications. The research the authors did highlights both the challenges and the consequences of vulnerabilities in these environments. BASE successfully uncovered previously unknown flaws in real-world BAS products, demonstrating not only technical feasibility, but also the real-world risks posed by insecure automation systems. The paper is a recent one. It appeared in the 2024 ACM SIG SA Conference on Computer and Communication Security. And as we'll see, it represents a significant step forward in the state of the art in fuzzing. In this presentation, we'll examine an introduction to fuzzing to kind of set the ground for what follows, then a paper overview, a problem statement in the paper, the overview of the author's solution. We'll get into a few details on case studies, discuss the results, and finally have a conclusion. So what is fuzzing? Before we begin, let's go through what fuzzing is. It's an automated software testing technique used to discover vulnerabilities. It works by inputting large volumes of malformed, unexpected, or random data, we call that fuzz, into a system or application. The goal is to trigger unintended behavior such as crashes or memory leaks or security flaws. In the context of network systems, fuzzing often targets protocol implementations, sending malformed packets to evaluate how a device handles abnormal input. It's especially valuable for identifying zero-day vulnerabilities in closed source or complex systems, those systems where traditional testing methods fall short. Fuzzing is widely used in secure development pipelines and has proven effective in uncovering critical bugs in operating systems, in browsers, in IoT devices, and in industrial control systems. This is a well-known approach to vulnerability testing, but as we'll see, the authors have found ways to improve on those basic techniques. The paper begins by placing its contribution in the context of a rapidly expanding industry. The global smart building market is projected to exceed $277 billion by 2027, with widespread adoption of intelligent systems to improve energy efficiency, security, and operational automation. Within these smart buildings, BAS platforms serve as the backbone for controlling essential services. These can include heating, ventilation, air conditioning, HVAC, lighting systems, motion sensors, fire alarms, door access mechanisms, and so on. As these platforms gain network connectivity and become more sophisticated, their attack surface correspondingly expands. The authors argue that despite the critical role BAS plays in facility management, these systems are often overlooked in cybersecurity planning. Many are built on outdated assumptions of physical isolation and trust, with little adaptation to the threat models introduced by IP connectivity. The combination of high value and weak protection makes BAS an attractive and accessible target for both external and for internal attackers. The work the authors did identifies a set of technical and structural problems in current approaches to BAS security evaluations. As BAS devices become increasingly connected via IP and wireless protocols, the likelihood of unauthorized access grows. The paper notes that anyone with access to a building's internal network, such as contractors, guests, or malicious insiders, could potentially reach these systems. The central technical problem addressed in the paper is that existing fuzzing tools are ill-suited for BAS environments. Traditional fuzzers assume the software under test is open source, file-driven, and will terminate on error, which allows for easy detection of crashes and tracking of execution paths. In contrast, BAS software is often closed source, event-driven, and is designed to run persistently, recovering from any errors. Furthermore, BAS protocols such as BACnet and KNX include complex field dependencies and require specific message sequencing and timing. Random mutation of packets by traditional fuzzers results in invalid inputs that are quickly dropped by target systems and yield little to no actionable results. The paper concludes that a domain-specific, building-centric solution is needed. The paper provides a detailed overview of standard BAS architecture to contextualize its methodology. Typically, a BAS network comprises three tiers: a client, a server, and the field device. The client is a workstation or control interface used by building operators. It runs specialized software to configure and monitor the system. The server, often an embedded device or gateway, mediates between the client and the hardware components throughout the building. Field devices include a wide variety of physical controls and sensors, such as thermostats, actuators, light switches, CO2 detectors, damper controls, and so on. Communication between these components is facilitated by domain-specific protocols. BACnet, developed by ASHRAE, uses an object property model. KNX, widely used in Europe, is structured around data points and supports tunneling, routing, and point-to-point messaging. What sets these systems apart is their tight integration with the physical world and the requirement for reliability. However, their complex message structures and real-time constraints make them particularly difficult to fuzz. The base framework is designed to navigate and exploit this architecture with precision. The design goals around BASE are built around three core goals, each addressing a specific challenge identified in the BASE security landscape. The first goal is that the framework must be able to automatically analyze and mutate complex packet formats. BAS protocols often rely on nested fields, context-sensitive metadata, and strict sequencing rules. The paper notes that malformed packets that don't comply with these constraints are rejected without any response, which hinders traditional fuzzing techniques and approaches. BASE addresses this by reverse engineering field roles within packet sessions to guide intelligent mutation. Second, BASE must support coverage tracking in closed-source client applications. BASE clients are typically proprietary and cannot be recompiled or instrumented easily. BASE overcomes this by dynamically intercepting system calls using binary instrumentation, allowing it to infer execution paths and detect crashes or hangs even in black box environments. Finally, the tool must maintain synchronization with low-throughput servers. Many BASE servers operate in constrained environments and only scan for inputs periodically. Sending packets too rapidly can overwhelm these BAS systems. BASE solves this by incorporating response timing information and adjusting its pacing dynamically, ensuring reliable delivery and evaluation of each and every fuzzed input. The framework introduced in the paper is modular and composed of four main components. First, the protocol analyzer. The protocol analyzer inspects captured sessions between BAS clients and servers. It dissects packets at the byte level to identify fixed fields that are magic bytes, dynamic fields that are length and counter values, and passive fields. It also determines necessary packet orderings to maintain valid protocol flows. These insights form the foundation of the fuzzing process. The core fuzzer uses the annotations made by the protocol analyzer to mutate packets in a structured manner. It avoids altering magic bytes and adjusts length fields as needed to match modified payload sizes. The tool includes probability models to determine when and how each field should be mutated, enhancing the likelihood of reaching new code paths. The client inspector focuses on fuzzing BAS client software. It attaches to the process, monitors network-related system calls, and records execution coverage based on observed activity. This is especially useful for long-running GUI applications or daemons with complex internal state. Finally, the server examiner performs server-side fuzzing. It sends inputs at a controlled pace, monitors for unique responses or crashes, and confirms whether the server remains responsive using heartbeat checks. Together, these components form a comprehensive and adaptive fuzzing framework for BAS networks. So how well does all this work? Well, as we've noted, the authors address the challenges of traditional fuzzers by introducing BASE. That's a protocol and timing-aware fuzzing framework that's explicitly designed for building automation systems. It departs from generic fuzzing techniques by embedding that deep domain knowledge we discussed about how BAS protocols operate and how their components interact. As we noted, the tool is capable of analyzing communication structures and protocols like BACnet and KNX, of dynamically identifying important packet fields such as counters, length indicators, and invariant headers. Additionally, BASE incorporates timing logic to ensure that fuzzed inputs align with the expected processing intervals of base servers, BAS servers, many of which operate on fixed scan cycles. So with this improvement in approach, the study reports that BASE was tested on a diverse set of BAS systems, and it uncovered 13 previously unknown vulnerabilities, including denial of service, memory corruption, and persistent crashes. These vulnerabilities affected both client software and embedded server devices. The paper also presents multiple real-world attack demonstrations. In one example, a single malformed BACnet packet rendered a BASE gateway completely unresponsive, which underscored the practical and immediate risks posed by vulnerabilities in smart building systems. Now that we've seen the overview of the author's solution, let's look at a couple of the case studies they did in detail. One of the case studies described in the paper demonstrates the real-world impact of a vulnerability discovered using BASE. The researchers targeted a BAS RTB router, which functions as a gateway between BACnet IP and BACnet MSTP devices. In the testbed, the router was connected to a temperature and humidity sensor and exposed both a BACnet interface and a web configuration panel. By sending a single BACnet IP packet containing a corrupted APDU payload, the researchers caused the router to crash completely. The device became unresponsive to both BACnet messages and HTTP requests. Crucially, the crash persisted across software restarts. The router could only be recovered by performing a full power cycle. The downstream sensors, although functional, became unreachable due to their reliance on the router. In a real deployment, this could lead to failures in climate monitoring, building safety, or building access. This example highlights how a low-effort, unauthenticated input, crafted through protocol-aware fuzzing, can incapacitate critical infrastructure with little chance of detection. It reinforces the importance of proactive vulnerability discovery in embedded systems. A second case study in the paper focused on a KNX-based system, the GDB 181.1e/KN damper controller. This device regulates airflow within an HVAC system and communicates through the LineMaster KNX IP gateway. Using BASE, the researchers crafted a routing indication packet with a malformed APCI prop value write command. The paper referenced an invalid property index, which caused the damper controller to become unresponsive upon receipt. What makes this attack particularly impactful is its repeatability. By resending the payload every 2 seconds, the researchers maintain a continuous denial of service state. The device did not crash in the traditional sense. It remained powered on and on the network, but it no longer responded to legitimate commands or configuration attempts. Such a disruption could significantly affect air quality, temperature control, and energy efficiency in a commercial environment. It also demonstrates the stealthy nature of these attacks. Since the device appears to be online, the issue might go unnoticed until environmental conditions degrade. The authors used this case to underscore the broader point that they were trying to make. In smart buildings, things are vulnerable not just to exploits, but to malformed inputs that evade traditional detection mechanisms. The paper presented a comprehensive evaluation of BASE across a diverse set of real-world BAS deployments. Testing was performed on 11 server devices and 6 client-side software frameworks. These included commercial-grade devices from Siemens, Greystone, Weinzierl, and others, covering both BACnet and KNX environments. BASE identified 13 previously undocumented vulnerabilities, 8 on the client side and 5 on the server side. The reported issues included memory access violations, segmentation faults, process crashes, resource exhaustion, and denial of service conditions that required physical intervention such as power cycling. To quantify fuzzing performance, the authors selected the popular open source KNX daemon KNXD as a benchmark. Over a 24-hour session, BASE discovered 17,616 unique coded execution edges, a metric indicating depth and variety in exercise program paths. The framework maintained an average rate of approximately 139 executions per second, balancing input diversity with the strict timing requirements of BAS targets. The study further compared BASE with BuFuzz, a general-purpose fuzzer. BuFuzz was tested under 2 configurations, the first with 0 protocol knowledge, and the second with structured packet information. In both scenarios, after sending more than 2.8 million messages, BuFuzz failed to uncover any vulnerabilities. In contrast, BASE was able to find bugs in as few as 50,000 targeted messages. The result highlights the importance of domain-specific fuzzing strategies. especially when working with complex real-time embedded systems where naive fuzzing approaches are often ineffective. The authors emphasized that all testing was conducted under strict ethical guidelines. Experiments were performed exclusively in controlled environments on hardware and software systems owned by or made available to the researchers. No fuzzing was conducted on live production systems or on systems serving actual buildings. Following the discovery of vulnerabilities, the researchers adhered to responsible disclosure practices by contacting the affected vendors with detailed reports and technical information regarding each issue. Several vendors acknowledged the findings and have since released or are in the process of releasing patches and mitigations to address the discovered bugs. The study did not release exploit code or enable replication of the attack payloads. Its primary objective was to raise awareness about security blind spots in BAS networks and promote proactive defense strategies. The authors argue that frameworks like BASE serve a vital role in bridging the gap between traditional software testing and the cybersecurity needs of embedded infrastructure critical systems that now operate on public or semi-public networks. In conclusion, the paper introduces BASE as a novel contribution to the field of fuzz testing and cyber-physical security. BASE is the first framework purpose-built to evaluate the security of building automation systems by accounting for their unique combination of protocol complexity, closed-sourced software, and timing constraints. The findings demonstrate that BAS environments, are vulnerable to relatively simple, unauthenticated inputs, many of which result in high-impact outcomes such as system crashes or persistent denial of service conditions. The authors demonstrated that by integrating protocol structural awareness, sequence dependency tracking, and input pacing based on device scan cycles, it is possible to perform highly effective fuzzing in systems where traditional fuzzing tools fail. Looking forward, the authors proposed several avenues for future work. Those include support for BACnet SC, a secure variant of BACnet that uses TLS in a public key infrastructure. They also proposed deeper integration with firmware rehosting and emulation tools to allow more invasive testing of closed-source BAS servers, and further generalization of the fuzzing engine to accommodate other cyber-physical domains. The authors see the study as serving as a call for action for increased attention to the security of building automation and smart infrastructure, a field that remains under-scrutinized in the author's opinion despite its growing importance.